Hello everyone, I'm Yuanfu, a PhD student from NYU. Today I will present our work, Mario Multimodal Graph Reasoning with Large Language Models. This is a collaborative work from NYU Shanghai, NYU Tsinghua University, and EPFL. In this work, we study how to enable large language models to reason over multimodal graphs. Most existing vision language methods focus on isolated image-text pairs. They learn local alignment between one image and one text description, but ignore broader contextual dependencies among different entities. This limits their ability to reason over structured multimodal data. However, real-world multimodal data rarely appear in isolation. They're often connected by rich relations, naturally forming multimodal graphs. For example, in an e-commerce graph, each node is a product with an image and a text description, while edges represent relations such as co-purchase. So the model needs to jointly handle multimodal attributes and graph structure. When we move from isolated pairs to multimodal graphs, the first challenge is weak cross-modal consistency. This means the text and image of the same node may not express exactly the same semantics. The image is not simply a rendering of the text, and the text is not simply a caption of the image. To verify this, we measure the cosine similarity between text and image embeddings. We compare frozen clip, tuned clip, and Mario. Frozen clip reflects the original image-text alignment. Tuned clip performs node-level tuning, and Mario further uses graph topology during alignment. The results show that raw image-text pairs in MMGs are poorly aligned. Node-wise tuning improves the similarity, but Mario improves it further by using graph context. For example, on movies, Mario improves from around 54% to 66% over tuned clip. This shows that neighboring nodes provide useful context for cross-modal alignment. The second challenge is heterogeneous modality preference. Different nodes may rely on different modalities. Some nodes are text salient, some are image salient, and some require both text and image. Therefore, using one fixed prompt template for all nodes is suboptimal. This Venn diagram compares three prompt templates: text only, image only, and text plus image. Their correct predictions do not fully overlap. Some nodes can only be correctly predicted by specific modality views. This suggests that fixed prompts can miss node-specific evidence, so we need adaptive prompting. To address these challenges, we propose Mario, a two-stage framework. Stage I is a graph-conditioned vision language model. Instead of aligning text and image independently, it injects graph topology into the encoding process. Then, a contrastive loss aligns the graph-conditioned text and image embeddings. This produces representations that are both modality-aligned and structure-aware. Stage 2 performs modality-adaptive graph instruction tuning. Based on the aligned features from Stage 1, Mario builds three prompt views: text only, image only, and text plus image. Each prompt also includes selected neighbors as graph context. The key idea is to route each node to its most suitable modality view. For this, we design a modality-adaptive prompt router. The router takes the node's text embedding, image embedding, neighborhood context, and structural information as input. It outputs a probability distribution over the three modality views. In this way, Mario can model node-specific modality preference. During training, Mario uses soft routing. All three templates are evaluated, and the LLM losses indicate which modality view works better. The router learns to match this performance-based distribution. During inference, Mario uses hard routing, selecting only the best template, so inference cost is comparable to a single template method. Here are the in-domain results. Mario consistently achieves the best performance on both node classification and link prediction. The gains show that simply concatenating text and image is not enough. Structure-aware alignment and adaptive modality routing are both important. We also evaluate generalization and zero-shot transfer. In mixed training, Mario remains strong across multiple datasets. In zero-shot transfer, Mario also clearly outperforms baselines on unseen graphs. This suggests that Mario learns transferable multimodal graph reasoning patterns. The ablation study further validates our design. Replacing the graph-conditioned VLM with GCN, GraphSage, GATV2, or MLP leads to lower performance. Also, no fixed prompt template is consistently best. Mario outperforms all fixed templates, confirming the benefit of adaptive routing. To understand the router, we visualize its selections on two graphs. Each color represents one selected modality view: text, image, or text plus image. The selections are not random. They form structured regions in the graph. This reveals a homophily-like pattern. That means nearby or connected nodes tend to prefer similar modality views. For example, in the highlighted regions, several connected nodes are routed to the same modality. This is reasonable because connected products often share similar semantics. To conclude, Mario addresses two challenges in multimodal graph reasoning: weak cross-modal consistency and heterogeneous modality preference. It first aligns text and image under graph topology, then adaptively routes each node to its best modality view. Experiments show strong performance across in-domain, generalization, and zero-shot settings. Thank you, and I'm happy to take questions.